Next talk is by Ken Diamond on mesoscale ionospheric sensing using modern radio interferometers.
Okay, today I'm going to be talking to you a little bit about measuring mid-scale ionospheric structures using modern radio interferometers. This is a topic I got involved in, I guess, about 4 or 5 years ago. Normally I work in the ultraviolet business and do mostly space-based measurements of the ionosphere. So getting to a ground-based kind of application and dealing in the radio is something totally different for me. What I'm going to be telling you about is, this is kind of a little bit of a science highlight and maybe perhaps a bit of a salesman job. Probably half bad, or not half bad at either one of them, but anyway. Basically, what our interest, whoa, wrong slide. What we're interested in is really trying to push the imaging capabilities of modern radio interferometers that are used for astrophysical imaging. And there are a whole slew of new interferometers that are being built. And these are incredibly large. You know, if you've ever encountered the VLA down here in southern New Mexico, you know, you encounter something that's just awe-inspiring because it's so huge. The new ones they're talking about are much bigger than that. Some of these with square kilometer, like here, the square kilometer array, with a square kilometer of collecting area. Ionospheric effects are important for all of these applications. And the interesting thing is what the astronomers have been doing is actually calculating and basically removing the ionosphere from the measurements to improve the imaging. And they're looking for people to use the data. And also, the astronomers are looking for people to work with them to try to improve their approaches. Now, this is a little bit of a slide that people have probably seen pieces of this before at various meetings. But this is a set of measurements made with the VLA down here in southern New Mexico. This is looking at a single bright source on the sky. And effectively what that does is back illuminate the ionosphere. And you're seeing the positions of 3 antennas that are separated by 8 kilometers along each of the 3 arms, roughly northerly, southeast, and then southwest. And you see a lot of different ionospheric structure shows up in these kinds of images. You see degradation, or essentially a decay of the ionosphere. You see some scintillation type things. You see a long period of quiescence, and then you begin to see the ionosphere perk back up again as the ionization kicks in at around dawn. And then you see TID effects showing up. Now, the astronomers, if you look at this image over here, this is essentially 9 panels that are made of looking at bright sources in the field of view of the VLA. You see here, this is a typical double-lobed radio galaxy here. You see these sources are wandering around, and that's effectively refractive wander. And so, and that refractive wander can be pretty severe. This is on the order of a few hundred arc seconds total wander over a period, and I've forgotten how much this is, but it's on the order of probably an hour's worth of observations. So this is essentially akin to standing at the pool side and looking down and seeing lights at the bottom of the pool move around as people splash and move, you know, waves are created. And that's the kind of thing that you see through the ionosphere. So, without getting into too much of the math, and you'll have to forgive me, there's a little bit of a translation error here between Mac and PC. But effectively, the important thing is that the astronomers are interested in determining the brightness distribution on the sky. They're looking at a surface brightness, okay? And the way they do it is actually by measuring what they call the source visibilities. They're actually measuring the interferogram at a given wavelength or frequency. This is at a fixed, fairly narrow band frequency, quasi-monochromatic. And this is the standard measurement equation that they've derived. And you can see that this is essentially a Fourier transform type pairing between the brightness on the sky and the fringe visibility. In this figure, S is a unit vector that's pointing toward the source on the sky, and R1 and R2 are essentially the positions of 2 antennas in the array. So the important thing is that you essentially have additional sources that creep in, or sources of measurement error that creep in. And these things can be as simple as geometric delays. Essentially, the source is off at some direction and it's essentially at infinity, so you have plane waves coming in, and you can have these geometric delays. This is actually an important feature, and it's exploited in aperture synthesis astronomy. You also have point spread function effects of the arrays. This is one of the, presumably the dominant lobe, and then all the side lobes. And then there's an assumption that's typically made in astronomy that there's nothing between the source at infinity and us. In fact, that's probably not really true. In fact, we know that's not true. But you're really interested in measuring the flux at Earth, so you can kind of ignore the stuff outside the atmosphere. The problem is the ionosphere violates this assumption. So if we go back to our measurement equation, effectively what happens is, if this is a true measure of brightness on the sky, and you're making your measurements at this equation, the way I've written it right now, is for a single measurement between two antennas, essentially a correlation between two antennas, and looking at a single bright source in the sky. That makes the math a lot simpler and cleaner for us to look at. But you essentially end up with these additional antenna terms. These terms contain, they're antenna gain terms, as the astronomers call it. They contain things like the point spread function of the antenna, which is actually pretty well known. They usually typically measure that in some way. And then a bunch of additional phase terms that get added into the mix. Two of them that are important for us here are the 2 pi phase ambiguities, and I'll get to that again, touch on it again later, in the ionospheric phase. These other terms, the geometrically induced phase, this is typically the Earth's rotation, that's actually used and exploited to basically get better coverage of the Fourier space, so that you can get better, when you try to essentially Fourier transform and recover the sky brightness, you can get much higher spatial resolution then. And then the other things are phase terms related to the antenna phase delay, maybe temperature induced, and et cetera. And if you're interested in some of the math and so on, I have this all attached at the end. I'm not going to talk about it in this talk. But if you're interested, you can look at the thing online afterwards. But effectively, these things, when they're substituted in here, they end up with phase differences between them. And so for the ionospheric phase, you end up with an equation that looks like this, that's related to the change in the TEC, where the TEC here is given in TEC units. And at the lowest frequency that the LWA, or excuse me, the VLA currently operates at 74 megahertz, that gives you a sensitivity of about 0.0015 TEC units per degree of phase. So you can do some incredibly precise ionospheric measurements with these. The unfortunate aspect is, because it's a phase difference and it's a TEC difference, you can't see an absolute TEC. You can only measure relative, or see the effects of relative TEC. So in building these large interferometers, and how does it affect us as ionospheric scientists, you kind of have to figure out or take a look at how the measurements are actually made. When the VLA or one of these, or if you look at a single station, for example, in some of these new interferometers, when the antennas are fairly clustered fairly closely together, and you're looking at a single bright source on the sky, you can see essentially, you can basically calculate what the ionospheric effect is for each of these and correct for it. In the newer cases, and actually some cases where in the VLA, when you're in the largest configuration, you're 40 kilometers essentially between the largest spacing between antennas, you end up with a case like this where you can actually have quite different ionospheres over the two. And so there you really have to start worrying about things like the phase ambiguities and et cetera. But it turns out that these two cases, let me go down and talk these others before I go on. This is a case that's also commonly seen at the VLA, where you're trying to image over the entire field of view. The VLA field of view is about 12 degrees on the sky, and that gives you roughly about I've forgotten, it's on the order of 100 or so kilometers pierce point across the sky. And the maximum separation of the antennas is on the order of 40 kilometers. So you can actually image over a fairly large chunk of the ionosphere. And now in the newer interferometers, you're actually talking about antennas that are, or stations that are widely spaced, and they'll see very different sections of the sky. So effectively, the astronomers have come up with good ways of dealing with scenarios 1 and 2. It's, you essentially calculate what the ionospheric phase is. You can actually solve that by taking all the antennas and calculate the individual ionospheric phases, correct for that, and then remove that before you actually do the Fourier transform imaging. And this is the technique known as self-calibration. It's the most powerful technique they have for correcting for ionospheric effects. In scenario 3, this is the kind of thing that's normally seen at VLA now, where you're trying to image very large sources on the sky at very high precision. The correction here is actually done in image space. So that movie I showed you on the first or second slide or whatever, where you see all the sources moving around, those are actually based on individually imaging the sources before the ionospheric correction is applied. And the approach here is to fit a phase screen and use that to minimize the image distortions, and then apply that to the visibilities, and then Fourier transform, and then co-add the images, and et cetera. And this is another powerful technique known as field calibration. The problem is the new arrays are having to deal in scenario 4, and no one has really come up with a good way to deal with this yet. And this is something where some enterprising student could come along and maybe make a name for themselves or whatever. So where do we go? Self-calibration, that's been shown to work over narrow fields of view, bright sources. Field calibration, wider field of view. Hybrid schemes are now being developed, and these include things like peeling, where you do self-calibration on the bright sources in the sky, and then you gradually start removing their effects and gradually working your way down to apply field calibration to remove most of the distortion. Two approaches we've tried with the VLA are data assimilation. We've done assimilations using IDA4D, and actually it was the University of Texas that done that. There's also been some work done with GAME, where we've done some comparisons with the Utah State GAME Gauss-Markov model. And these do show some promise, but we essentially need to feed a lot more data in the regional sense to try to pin things down. The other approach we've been looking at NRL is looking at the phenomenological approach, where we're trying to identify particular phenomena and then to try to tailor the corrections based on that. So as an example of this, one of the first things we did, or maybe not one of the first, but one of the more recent things we did, was to try a campaign where we actually used VLA on the ground and made ionospheric measurements during an overflight of the COSMIC, or one of the COSMIC satellites. We were looking at a bright radio galaxy, 3C124, which for all intents and purposes is a point source. So we could use the self-calibration technique. And then we were looking at essentially limb occultations, and deriving vertical electron density from inversion of limb occultations made with the COSMIC satellite. And then we also used the UV photometer on there. This is just an example of some of the data from COSMIC. These are a set of the occultations that were made, and these are essentially the electron density profiles produced by Abel inversion of those profiles. And you can see on this particular day during this campaign, the ionosphere was actually pretty quiescent, and there was very low gradient in this region, height-wise and density-wise as well. These are what the VLA measurements look like. And essentially, these are phase measurements made relative to the center of the array. And what I've done here is to divide by the baseline length. And what that does is to basically back out what the change in the relative TEC is looking like. And you do this to see if you can actually, if you see any great deviations from one antenna from another, Usually what will happen is you'll see a set of antennas and then you'll see a cluster with another phase. That's an indication that you have a phase wrap somewhere in the system and you have to remove that out. But everything, you can see that there's a TID coming through here, or actually probably more than one because of the structure. So let me go back one. So essentially what the next step was is to Fourier transform all of these in the time domain and to determine what the frequency, the TID spectrum looked like. So you get a TID velocity, direction, et cetera, from that. So the approach is fast Fourier transform, and then you go back and try to do a fit in the spatial plane at each of the frequencies to derive the directions of the phase front. And this is the results of that analysis for that previous data set. And you can see typically what you're seeing here in this observation was a set of, you see a significant power at all of these different periods that are consistent with what you typically see in mid-scale TIDs. So what we derived here was a period in minutes, the amplitude, wavelength, azimuth, speed, and et cetera. And basically, we're seeing speeds that are typical of MS TIDs, wavelengths on the order of 1 to 200 kilometers, periods in the period range of 1 to 10 to 100 minutes. And the direction of propagation is typically southwesterly, but not always. I didn't talk about that carefully, but here's an example here. Here's a southwesterly traveling wave. These two here are traveling more southeasterly. So you're actually seeing quite a lot of structure passing overhead. Now this is the UV data from the UV photometer that's looking downward. This measures the decay of the ionosphere. Okay. And at 1356 angstroms. And so you can actually model this and invert it to get what the vertical TEC looks like. This is the section of the MS-TID that was basically photographed, or however you want to look at it, observed by tip. These are the radiance measurements. And you can see the tip measurements had a very, very high sensitivity. So these are the error bars. These are actually 4 sigma error bars, plus or minus 2 sigma. So you can see that it's very high sensitivity. The TEC that you were seeing in this particular event was only on the order of between 4 and 8 TEC units. So it's not very strong ionosphere. If you Fourier transform this packet, these are the wavelengths you get out. And these actually 3 wavelengths, or 3 of the wavelengths that came out of the Fourier transform analysis of VLA data. So you're seeing something that's consistent between these two instruments. So this is an example of the kinds of things that you can do with TIDs and somewhat smaller structures by analyzing the data. We tried to figure out where this thing, what's a possible source of origin for all of these waves. And it turns out that if you go online, you can find these very nice maps of the jet stream. And so you can see the jet stream here has this U-shaped structure over the U.S. This little lambda picture here is the location of the VLA. And so there's some structure, there's something going on here in the jet stream that could potentially be producing gravity waves that are passing up into the lower thermosphere and generating these TIDs. Another example of things, another campaign we had done was to try this with an all-sky camera. We actually had a serendipitous all-sky camera measurements during the cricket campaign, but there were some issues with the measurements, and so the data didn't pan out. But here's an earlier episode that we tried. And here's an example of some of the all-sky measurements. Here's, this is 5577. You can see there's 50 kilometer wave structures here at one time. Later, structures on the order of 10 kilometers. And basically, this suggests that there's a possibility of sporadic E. Here's some examples of sporadic E measurements that were made with the VLA and correlated with measurements made elsewhere at Port Arguello and at Dias Air Force Base ionosons. So there was definitely sporadic E appearing that night. So basically, what's the next step? Well, southern New Mexico, this is a picture of the the LWA, the long wavelength array. These dots on the state of New Mexico here are the locations, of the proposed locations of the antennas or the stations for this. This is going to be a much larger array, and it's going to operate at 20 to, I forgot what it was, 20 to 80 megahertz essentially. They intend to produce ionospheric measurements all the time using a technique where they rapidly scan the sky. This is a phased array antenna, and they rapidly scan the sky every, roughly, it takes them about 6 to 7 seconds per scan, and they typically hit about 100 sources. And so effectively you can get self-calibration type measurements all over the sky. No one has actually started to exploit this yet, although these measurements have been made. This is an example of how the kind of ionospheric coverage at 350 kilometer Pierce points. These are the 350 kilometer Pierce points of a simulation that's consistent with the kinds of measurements that they've been doing with the LWA so far. You can have a huge number of lines of sight. They're typically working with the VLA sky catalog, or VLSS sky catalog, and it's got 16,000 sources on the sky. So, so effectively, modern array interferometers are very sensitive to the ionosphere. You can do, the unfortunate problem is you can only measure the TEC difference between the elements in the array, but they're incredibly sensitive for that. They have high temporal resolution. It can be on the order of 10 seconds. Typically, with VLA measurements, we normally operate on the order of a minute or so, but they can be faster. LWA is set to go with about a 10-second highest rate for measurements. You can get easily measured TIDs. There have been a lot of studies of that. The sporadic-E ionospheric gradients, you can study the evolution of those things. You got high spatial resolution on the order of tens of kilometers and maybe higher. Smallest spacing that you have currently in the EVLA is on the order of 400 meters. So basically the next step is we need new ionospheric correction techniques, and we're hoping as astronomers that the ionospheric community can step up and help with that. On the other side of the coin, this provides a unique opportunity for us making ionospheric measurements to work with the astronomers and to try to get all the ionospheric data, or the ionospheric data that's produced. And also, I think this potentially is a nice opportunity for a student or postdoc or whatever to step up and develop some of these techniques and perhaps make a name for themselves, as I mentioned earlier. For those of you interested in looking into this a little more detail, here's some references. I strongly recommend this one here, the first one. It's got a really nice overview of everything. Here's some of the more sciencey references, and I'll leave you at that.